It is October 26, 1676, and Isaac Newton is writing a letter to his great rival Leibniz. He wants to talk about his greatest discovery, but at the same time, he wants to keep it a secret. So instead, he sends a riddle. 6a, 2c, d, ae, 13e, 2f, 7i, 3l, 9n, 4o, 4q, 2r, 4s, 8t, 12v, x. Leibniz did not decode this message, but science historians have now decrypted the Latin phrase that was hiding in the anagram.
Data equazione quodcunque, fluentes quantitates involvente, fluxiones invenire et vice versa.
In English, given an equation in any number of variables, find its derivative and vice versa. This is the differential and integral calculus, a crystal ball that is incredibly effective for predicting the future. It lets you calculate the future movement of a system when you know its present state and the forces that act on it. It is about solving a differential equation and finding solutions. Let's look at this in a world made of Lego. After all, the mathematical world is a bit like a game, where everything is simpler than in real life, a world that is sometimes even a bit childlike. The footprints indicate the paths followed by the athletes, their trajectories. Suppose that our Lego athletes take steps at a steady pace, but some have steps that are long, while some have steps that are short. For the athletes that go quickly, two consecutive footprints are far apart. For the ones that go slowly, the steps are close together. The arrow joining two consecutive steps indicates the speed. It is the difference between two positions at two consecutive moments, hence the phrase differential calculus. A 100-meter race. Who will win? .58 seconds. Bravo! Now, movement rarely consists of discrete steps. Consider these moving race cars. They roll, they don't take steps. What then do we mean by speed? One idea is to recall that this film consists of 25 frames per second. So we can think of the motorbike as taking 25 steps every second. Hence, we can talk about its speed, just like we were talking about the speed of the Lego runners. Newton approximates any continuous motion as a sequence of stepwise movements, but with steps that become so small that they become invisible, just like in the movies. Calculating the speed of a motion is called calculating a derivative. It is the goal of differential calculus. Here then are some movements. These arrows indicate the speed, and mathematicians call them vectors. Now imagine the opposite problem. Look at the arrows drawn on the floor. Mathematicians call this a vector field. Imagine a field of wheat, but instead of stalks of wheat, we have vectors. The Lego people's mission is to move with speed as indicated by the vector field. Easy, you say. They look under their feet and they see a vector, which tells them how to move. Then they set off in that direction and at that speed. A brief moment later, they've arrived at a new point with a new direction and speed, and off they go again. They do this over and over again. Walking is not difficult. Just put one foot in front of the other and do it again. Actually, we should explain what we mean by a brief moment later. Newton's answer would be an infinitely brief moment. We already saw that a continuous movement is not the same thing as a succession of steps. It's what you get when the steps become smaller and smaller. So, rather than hopping like a Lego person, take a car that rides continuously. You will follow what is called a trajectory, a curve that is tangent to the vector field everywhere. Here you have a vector field in the plane and 2 points that are the initial positions of the 2 motorcycles. The theorem of Cauchy-Lipschitz summarizes the concept of determinism. It claims that the starting points determine the future trajectories. From each point, there is a unique trajectory whose initial position is the given point. Each point has its destiny, different for everyone. The Lego man faces his fate. All he can do is follow his trajectory. Note that 2 trajectories can never cross. Determining the trajectory from the knowledge of the velocity field is the work of integral calculus. Thus it goes in the opposite direction from differential calculus. Here's a group of Lego people neatly ordered, our little soldiers ready to start walking. Off they go. You see that the nice original order gets destroyed. It is sometimes said that one determines the flow of a field as if these characters were floating on a river, each following their course in the current. Think of the flow of humanity, those 7 billion Lego people moving all over the Earth, or think of the flow of billions of billions of billions of molecules in the Earth's atmosphere. Here is a simple example, almost naive, which will show us a weakness of determinism. Watch this vector field. The figures move forward and, as you can see, those on the left of the central line turn to the left, and those on the right of the central line turn to the right. In a way, determinism is valid. Everyone follows his destiny over which he has no control. But on the other hand, 2 men starting very close to each other can have very different destinies. A little thing can completely change the future. In his little book, Matter and Motion, published in 1876, the physicist Maxwell stresses the sensitivity of physical phenomena to initial conditions. Here is what he writes. There is a maxim that the same causes will always produce the same effects. There is another maxim, which must not be confounded with the first, which asserts that like causes produce like effects. This is only true when small variations in the initial circumstances produce only small variations in the final state of the system. In a great many physical phenomena, this condition is satisfied, but there are other cases in which a small initial variation may produce a very great change in the final state of the system. For instance, a small difference in the speed of the car may cause an accident. This dependence of the future on initial conditions is only one aspect of chaos. But there are much more complex situations. Imagine, for example, a vector field which is no longer drawn on the ground, but is drawn in space. This one, for example, shown on a vertical plane moving back and forth. Now our Legos don't walk. Instead, they fly in their spaceships. At every moment, their speed is determined by the vector field. See what happens to our poor Lego astronauts. This is much more chaotic. Can we imagine a fortune teller who can divine the future position of the spaceship? It is impossible on such a roller coaster. His predictions would be mere deceptions. Where will the ship be in an hour? No one can tell. If it is difficult to predict the future of a Lego astronaut, just imagine predicting the future of a human being.